Okay, I think I will start. Good morning, everyone. It's my pleasure to welcome today's speaker, Maximilian Bachmaier. Maximilian obtained both his bachelor's and master's degrees in physics from Ludwig Maximilian University of Munich, where he is currently a PhD student. Since 2022, he has also been affiliated with the Max Planck Institute for Physics, working in the cosmology group led by Professor Gerda Valley. His research focuses on topological effects in direct dynamics, include magnetic monopoles, cosmic strings, and vortex, using a combination of analytical techniques and numerical simulations. He studies nonlinear phenomena in field theory and their implications for particle physics and cosmology. Today, we will give a seminar. He will give a seminar entitled The Importance of Resonance in Vortex Collisions. Please join me in welcome Maximilian Bachmaier, and thank you again for accepting our invitation. You can start. Thank you.
Thanks a lot. Thanks for this very detailed introduction, and also thanks a lot for the invitation. I'm very happy to present you today two papers that we published within one this year and one last year. And the topic of the talk basically is about the importance of resonances in vortex collisions. So vortex collisions are already a topic that were discussed for a long time, for the last 40 years, basically. But recently, approximately 2 years ago, it was found that in vortex collisions, resonances play a very crucial role. So when two vortices, for example, collide, or resonances also play a very crucial role in vortex-antivortex collisions. And these topics I want to explain here in this talk in a bit more detail. So these are two projects that were in collaboration with Alberto Alonso Izquierdo and Andrzej Vereshczynski. Okay, before I go to vortex collisions, let me first briefly introduce what actually vortices are. So in this talk, I will always focus on a abelian Higgs model given by this Lagrangian here. So we have one complex scalar field, and the theory is gauged. So we have one gauge field, one U1 gauge field, and the field strength is the gauge field of field strength is the gauge field. This is the field strength. The F is the field strength of the gauge field. Okay, now in this theory, because of the form of the potential, the U1 symmetry of this theory gets spontaneously broken down to U1 when phi is getting a vacuum expectation value. So this means that the vacuum manifold is a circle, and the first homotopy group of this vacuum manifold is non-trivial and is given by Z. So they are non-trivial mappings from the boundary of, let's say, a two-dimensional space to the vacuum manifold. And these mappings are these so-called vortex mappings. So a mapping like this could look like this here. So at r goes to infinity, so at the boundary of our spatial space, there can be a mapping from the boundary down to the vacuum manifold. So and this mapping could look like this. So e to the I n phi, where n is some integer and phi is the polar angle around the origin. Okay, this means, for example, if I have here a two-dimensional space, it can be that each of these four regions can be mapped to a different point on the vacuum manifold. And if there's some winding, you get this Nielsen-Olison vortex solution. Okay, so the full Nielsen-Olison vortex solution has the following structure. So this is exactly this mapping that I just showed, but you can also multiply a profile in front of it such that the solution is valid everywhere in space and not only at r goes to infinity. Additionally, to minimize the energy, one not only has the scalar field that is non-trivial, but also an extra contribution from the gauge field. So the full Nielsen-Olison vortex solution looks like this. We have a phi component, and we have a phi field and a phi component of the gauge field that is also non-trivial. Because of this gauge field, the vortex also contains at the end a magnetic flux. And the magnetic flux is given by 2 pi times the winding number. So a vortex with winding 1 would have a magnetic flux that goes, for example, the points outwards of the plane, and a vortex of -1 will be a configuration where the magnetic flux goes into the plane. So this is the solution of this non-abelian Higgs model. Okay, now here we have only one vortex, but in principle, we can also have multi-vortex configurations, so multiple vortices. And to get these multi-vortex configurations, one can use a product ansatz of these scalar fields, where each of these scalar fields here, so describe a vortex at x1, for example. Here we have a vortex at x2. And for the gauge field, we just add them together. So it's very easy to get from one vortex solution multi-vortex configurations. It's just this product and summation ansatz. For monopoles, for example, the situation is way more complicated, but about this I could give a full talk, and this is a story for another time. Okay, good. Now when we have this multi-vortex configuration, let's consider for the moment just two vortices. So if we take two vortices, then the two vortices interact with each other because there are two kinds of forces. So we have the scalar force and the gauge force. So the scalar force usually for vortices is always attractive, and the gauge force is for a vortex and a vortex of same winding repulsive because the magnetic flux is pointing in the same direction. So it's like two vortices of same magnetic charge, if you want to call it like this. So we have a repulsive gauge force and an attractive scalar force. Usually, these interactions are exponentially suppressed because all degrees of freedom here in this theory are massive. So the Higgs boson is massive and also the gauge boson is massive. So they are exponentially suppressed, but in principle, you can still feel some interaction when the vortices are closer together. Now, we have three parameters in the theory. We have the gauge coupling G, we have the vacuum expectation value V, and the scalar coupling lambda. And without loss of generality, you can always set the G and the vacuum expectation value just to 1, because you can rescale the theory, just that the dynamics depends at the end only on one parameter, which is lambda, so the scalar coupling. Now, if the lambda is smaller than 1, then the scalar core is bigger than the gauge core. This means that the scalar interactions have a longer range than the gauge interactions. And if you have two vortices, this means that the scalar force dominates and two vortices get attracted to each other. If lambda is bigger than 1, it's the opposite way around. So the scalar core is smaller than the gauge core, which means the gauge interactions are more dominant, which means that the two vortices will repel. And at lambda equals 1, these two, the scalar and the gauge core, have exactly the same size, and the force exactly cancels each other, which means two vortices will not really feel each other. It doesn't matter where you place them, they always stay at the same position. There's no force between these two vortices. And in the first part of my talk, I will focus specifically on this case where lambda equals to 1 on this BPS case. Okay, so I will present two things. So the first part of the talk will be about collisions of multiple vortices, especially also when these vortices are at the end excited. And the second part of the talk will be about vortex-antivortex collision. So let me focus first on multi-vortex collisions. For this, we start again just with two vortices. And although there are no forces between a vortex and vortex, they will still interact with each other when they collide with each other. And to understand what happens at the collision, I have to introduce very briefly the moduli space approximation for two vortices. So first of all, what are collective coordinates? So collective coordinates are coordinates that describe a full class of solution that are the generated energy. This means, for example, if I have one vortex, it doesn't matter where I place it. It doesn't matter what the position of the vortex is. The energy of this vortex and the structure of the vortex is always the same, which means that the position, so the coordinates of the position, which are two coordinates in a two-dimensional space, are collective coordinates. They describe basically the position of the vortex. And then the moduli space is spanned by all these collective coordinates. So the moduli space is the space that is described by all collective coordinates. So for one vortex, we have a two-dimensional moduli space. For two vortices, it's a bit more complicated, because for two vortices, we have now, we can place two vortices wherever we want. So in principle, we have four collective coordinates, but only, the moduli space at the end has a very rich structure in the BPS limit, which means if there are no forces between them, the configurations are really the generated energy. Because if you have a force between vortices, the energy will be different with different distances. So in the BPS limit, we really have four collective coordinates. Additionally, what the moduli space approximation usually assumes is that the vortices are also moving very slowly, because otherwise you also have some Lorentz contractions that needs to be taken into account, and this makes the story way more complicated. So we will consider the BPS limit and slowly moving vortices. And in that case, the moduli space has the following structure. It's R2 cross R2 over Z2. So what this actually means is the following. So the R2 describes two collective coordinates, which describe the center of mass. So I can have the two vortices and I can move them around as I want. And these are two collective coordinates. This describe exactly this two vortex configuration, just moving around without changing the distance, for example. Then the R2 over Z2. So this Z2 means that we have two indistinguishable vortices. So if I exchange them with each other, I get exactly the same configuration. So we want to exclude a half of the configurations because they are just exactly the same. That's why the Z2 is appearing. And the most interesting part in this moduli space is this combination, this R2 over Z2. So this R2 over Z2 describes two collective coordinates. So one coordinate is the distance between the vortices, and one is the angle, how you rotate these vortices. And in the following, we want to discuss for the moment only the distance. We want to see, okay, when the distance is getting smaller, what happens with the vortices at the collision? And you can imagine this part of the moduli space now in the following way. So if you work in the center of the mass frame and you have two vortices, I can move the vortices around, but the position of one vortex is enough to always know where the other vortex is, because you're in the center of mass. So if I move one vortex to the right, the other one has to move to the left, for example. So because the center of mass is fixed at one point. This means that only half of the space here is enough to describe the full configuration. So now, this means half of the space I can cut away, and these cropped edges here, I can glue together to form such a cone. And the moduli space will at the end have exactly such a conic structure. So if you analyze this in a bit more detail, you will find, okay, the tip of the cone is not very sharp, it's a bit rounded. So it looks more like this here. And then at the end, geodesics on this moduli space, geodesics on this rounded cone, describe at the end trajectories in my real space. And the simplest geodesic is just the line that goes over the top of this cone here. If I now translate this back into my target space, so if I unfold the cone again, this would correspond to this yellow line here that changes here the direction by 90 degrees. Which means if we have two vortices will scatter by 90 degrees. So this is what the moduli space approximation for two vortices at the end predicts. Okay, we can also now simulate this. So this is a simulation where we have two vortices. These vortices scatter, and when they collide, we can really see they scatter by 90 degrees. All these things can be now done also for multiple vortices. For example, with three vortices, you can have this triangle scattering, or you can have this collinear scattering, and we can use the moduli space approximation to describe these scatterings here. So all these things can be predicted. And all these simulations were already done in the 80s and 90s. So people already knew how to simulate these things and how to predict it. So this what I showed so far is very well known. But 2 years ago, a new, let's say, research direction in vortex collision started, because there were two papers, one by Krush, Ruiz, and Vineyard, and the other one by Alonso Izquierdo, Matteo Schigliate, and Vereszczynski. So they studied a 1+1 vortex collision, but not just the vortex collision, they excited the vortices initially. So in nature, it's very natural that vortices are excited because you have a lot of thermal fluctuations in your systems, which means, okay, the thermal fluctuations can excite some modes on the vortices, and these modes, the vortices can, describe some, I will say more words about excitations in a second. So these are basically some oscillations on top of the vortices. And they found that these excitations change the dynamic a lot, how the vortices at the end scatter. So this was studied in 24 for a 1+1 collision. And last year it was also studied for three vortices, and this triangle collision that I just showed you, or this collinear collision. Okay, before I describe this in more detail, let me first tell you, okay, what actually excitations of vortices are. So what we want to do is we want to perturb the vortex, which means we have the vortex solution here. So this is the solution that I showed you already before. Just this phi vortex, which is this mapping from the boundaries of the space to the vacuum manifold, and the phi component for the gauge field. And now we want to add some excitations on this vortex. So we have here some profile functions, f and g. Psi is just an amplitude. So the bigger the amplitude, the stronger the perturbation is. And then the perturbation is time dependent with some frequency. So we have e to the I omega t here. Okay, now we can insert this into our field equations to get equations for f and g. So this would look like this here. So I don't want to explain these equations in full detail. So I just want to show you, okay, if you insert this, you get some equations that describe this f and g. And these equations, so these are the linearist equations, so we only analyze small perturbations. And these equations can be solved to find at the end what the frequency of the excitations of the modes of the vortices are, and also how the shape of these modes looks like. So we can do this numerically, and then one can find is that, for example, for the BPS vortex here, you get profiles that are more localized around the vortex and go to 0 at r goes to infinity. And we have one specific frequency in the BPS limit at lambda equals 1, which is given by omega squared as 0.77788. What you can also see from this plot here is you can solve this differential equation for the modes for different values of lambda. So you can go beyond the BPS limit. And you can see, okay, for small lambda, the frequency gets smaller. It goes down to 0 at lambda equals, lambda is going to 0. And the frequency grows for bigger lambda. And at lambda 1.5, it hits here the mass threshold. So these two lines are the mass threshold, which means, okay, above these lines, I can excite some modes of the continuum spectrum. So if we are, for example, here above this line, about this nv squared equals 1 line, this means the mode has a frequency that would be higher than the mass of the gauge boson, which means I can emit gauge bosons, and the mode will just decay very quickly, exponentially fast, because it's energetically preferred to decay gauge bosons in this regime. Okay, but below lambda 1.5, you have a bound mode where this is more suppressed, where this excitation into the continuum spectrum is more suppressed. Good. Now, how does this look like if you have two vortices? Because if you have a two vortex configuration, the frequency of the modes can change. So it's not only just a single vortex anymore. Now you have two vortices. If the distance between them is infinitely big, you have two isolated vortices, and you will get the same frequency that I just showed you. But if the distance is getting smaller and you have some overlap of the cores of the vortices, the frequency will change. And this is also something that one can calculate, and this is usually described by the spectral flow. So here in this plot, you can see on the x-axis the distance. So for the moment, it's only relevant to look on the positive d axis. And you can see, for example, for this blue line, if you excite the vortices in phase, so they have the same type of excitation, and they are synchronized, then you can see, okay, for smaller distances, the frequency of the vortices of the excitations changes. Here, large distances, you are at omega squared equals to 0.77788. And for smaller distances, the frequency decreases. Now, when the distance is exactly 0, you're here at around 0.5 something, which would be the frequency of the charge 2 vortex at the end. And this frequency changes continuously from this point to the case where they're infinitely separated. But now what does this mean? This means that because the mode itself, the excitation itself, carries some energy. You can imagine this as some mode potential energy. This means the higher the frequencies, the more energy is stored in the modes. So this means when the vortices are closer together, less energy is stored in the modes because the frequency is smaller. This means, okay, you can imagine this like a potential. So two vortices, in this case, when they're excited with this blue line here, they are attractive because it's energetically preferred to have them closer to each other because the frequency is lower. So, and this is what was found 2 years ago. So, in the paper by Stefan Krusch, Morgan Rees, and Tom Wynyard, they considered exactly this thing. They took two vortices, they excited it, and they saw, okay, these two vortices attract each other. They scatter by 90 degrees, but because of this excitation, they always attract each other and form a multi-bound state. Okay, now There's another case. You can also excite this two vortex configuration out of phase, which means the excitation is not synchronized anymore. Now it's exactly, so one excitation is actually shifted by a phase shift of pi. So you have an out of phase excitation. And this would correspond to this orange line here. So in that case, so if the vortices are excited like this, the vortices, so the frequency increases when the vortices come closer to each other, which means the energy would increase in the full configuration. And this means that the vortices will repel in this case. So in this case, the vortices will not attract, they will repel. Okay, so this was a very brief summary on what was known, what was found in 24 on 1+1 vortex collisions. And later last year, this was also studied for this triangle collision and this collinear collision. But all these configurations have one thing in common, and they have, so this is the following thing. So all these configurations can be described by a single parameter. So here in this 1+1 collision, you have only one parameter, the distance, that describes these configurations. In the triangle collision, you have the distance to the origin, or here in the collinear collision, you have the distance also to the origin. So in this, and this is the only parameter that describes all these configurations here. And this is because you have some specific symmetry. So here you have, for example, a reflection symmetry along the x-axis and the y-axis. You have the same also here. And the triangular scattering, you have a C3 symmetry. So you have very strong restrictions because of the symmetry. Now, what we wanted to do is we wanted to break the symmetry a bit more. We wanted to say, okay, what if we analyze configurations that have that are described by two parameters? And the most simplest excitation that is described by two parameters at the end is the 2+1 case. So a charged two vortex colliding with a one vortex, because this configuration has only a reflection symmetry along the at the x-axis, not at the y-axis anymore. Okay, so we wanted to study this, and it turns out it's not so easy to study this, because first one has to find the moduli, the geodesic on the moduli space. So this means we need a very nice way we need a good parameterization that describes exactly the subspace in which we are interested. Because a moduli space for three vortices usually has 6 dimensions. We have 6 collective coordinates that can describe this configuration. Now, 2 of them are the center of mass, so we can ignore them, and 2 other of them are we get rid of them by assuming that we analyze now only configurations that have a reflection symmetry along the axis, at the x-axis. Okay, so we need a good parameterization for subspace, and at the end what we found is we took this parameterization here. So I don't want to describe this in too much detail. So this just means we have 2 coordinates, A and B, that describe this configuration. For example, A always describes this distance between the vortices to the origin, and B describes the distance between the vortices that are closer to each other. So, and it turns out that these 2 parameters are enough to describe all the configurations that can appear in this 2+1 vortex collision. So here in this plot, we have, for example, 3 lines. So the blue line, for example, in this parameterization would be this triangle scattering. So this along this line, you're always on a triangle. Then this orange line here would be this collinear scattering that I already showed you before. And now the green line is the new case, which is the 2+1 collision. So we are on the positive a-axis when one vortex is on the right-hand side of the plane, and we are on the negative a-axis when only one vortex is on the left-hand side. So you see here in the beginning, we start with one vortex on the left, on the right-hand side, and at the end, we end with one vortex on the left-hand side. So this is when the A is changing the sign. What is also relevant to see is always when this green line is crossing the A-axis here, so B is flipping basically the sign, then we have a right angle scattering at the x-axis. So you see, okay, this crossing happens when these 2 vortices here scatter by 90 degrees. So the overall process looks as follows. So we have this one vortex and this charged 2 vortex, and this charged 2 vortex first splits along the x-axis, and then these 2 vortices perform a right angle scattering and move away to infinity. And now we wanted to see how these trajectories here, this green trajectory changes when we excite the vortices. Because for the triangle scattering and the collinear scattering, when we excite the vortices, what will happen is, okay, you have multi-bounces, like for the 1+1 collision, but the trajectories itself are always the same. So they move always along the trajectory, so always along the blue line or the yellow line. Now in the 2+1 case, we will see that this line, the full trajectory, the full geodesic, can also have different shapes. Okay, so to understand this, we first introduced again this spectral flow to understand, okay, if there's an attractive or repulsive force. This is quite complicated. Let me just tell you the main findings that we found here. So this is very similar to the case to the spectral flow that we already saw for the 1+1 collision, but now in terms of its A and B coordinates. So for example, if I excite the 2 vortex, the blue line is the relevant line, and this means, okay, we see the frequency will decrease when the configuration, when the 2 vortices come closer together, which means, okay, these 2 vortices will attract each other because of this excitation. The orange line would correspond to the line where the 1 vortex is excited, and in that case, the frequency will increase, which means the configuration is more repulsive. And we have also other modes which we have not excited in our simulations because they are quite hard to excite. Okay, so we are only interested in this yellow and the blue line. But it's easier to see just the result, so what is happening. So if we excite the 1 vortex, exactly, we get these deformations of the trajectories. So we see the black line is the one from before, and the higher the amplitude of the excitation is, the stronger the trajectory at the end is deformed. So first we have just a small deformation for small amplitudes, but this deformation can be also very strong. So let me show you some examples here. So we can see, for example, when the 1 vortex is excited, the trajectory is a bit deformed. So the 2 vortices that were in the beginning moving along the y-axis to infinity, they now also have a small velocity in the x direction. So the dynamics changes a bit. And if you excite them even further, you can see that they scatter for a second time. So the purple line crosses the axis again, which means we have 2 right angle scatterings. So there's also something that can happen. And if you have a very strong excitation, this is the extreme case, you also have here 2 right angle scatterings. They come directly back, and then you form a multi-bound state here on the left-hand side. Okay, so we see when we excite this 1 vortex, there are really strong deformations of the trajectory. And this is now a new result compared to the cases before, because now the vortices really move in a different way. They don't move just along the geodesic, they really change the full trajectory in the moduli space. Okay, let me show you also now some examples for the excited 2 vortex. So just 2 examples. So one case when it's excited with a low amplitude, we can have, for example, this scattering that the first 2 vortices want to go in the beginning into the direction of the positive y-axis, but then they come back, and at the end, again on the left-hand side, we have a bound state of 2 excited vortices. Or another case is when the 2 vortex is very strong excited. In that case, the final state is a bound state on the right-hand side. So you really see here very strong excitation. So you have multi-bounces in this charge 2 sector. So these bounces were already found 2 years ago, but now we see, okay, this is a result of this 2+1 collision. Okay, so summarized, what we found is excitations are really relevant in vortex collisions. They change the dynamics a lot, and because excitations are very natural in nature, you can have thermal fluctuations. It would be interesting how these scatterings at the end really appear in nature. So how thermal fluctuations really influence the dynamics, and maybe our findings can also give some hints in this direction. Okay, before I start with the second topic, I would like to ask you if you have some questions, because I will switch then the topic to vortex-antivortex collisions. So do you have any questions?
Yes, I do have it.
Hi. I'm sorry.
Yeah,
sorry.
Go ahead. No, go ahead.
No, please.
Ladies first. Go ahead.
Okay. Sorry. I have 2 questions. so this effect, that this deflection that you saw, that it's not exactly right angle when you increase the amplitude of the wobbling, right? The amplitude of this excitation. So
Yes.
was it
Yes.
for a small amplitude of excitation, it was right, perfect right angle, right? And
wait,
then
wait.
you increased, yes.
You mean here?
Like here. Yes,
okay,
exactly.
no, okay, it's not perfect right angle. It just looks like this, but almost right angle. Yes, I agree.
But I guess like in the limit A, the amplitude goes to 0, it becomes right angle, right? Because it is, you didn't excite the mode in the beginning. So you would expect the right angle because there is no impact factor, right?
No. This I agree. So here, in that case, now here you really have a right angle scattering.
Yeah,
yes.
It has a bit of deflection, I can see.
Yeah, exactly.
But
and this
not
is because of
much.
the other vortex there. You see that the left vortex is not stopping completely. It still moves a bit to the left.
Yes, exactly.
Right, that's why
and
it's not
in this
perfect
case,
here.
what is the amplitude of excitation, or there isn't?
In that case, there's no excitation at all. It's 0.
So it exists already when the amplitude goes to 0.
Yes.
Okay, but it becomes much more, pronounced when you increase the amplitude more and more, right?
Exactly. When
so
the excitation...
there is. So how is this? Is the, in this regime that you increase the amplitude, at some point the linear analysis with the modes breaks, right?
I agree.
Because the nonlinearity effect will be very pronounced, right?
Right, I agree. But at the end, we are solving the full equations of motion, right? So of course the initial ansatz is maybe not perfect anymore, but the collision happens way after we insert the vortices, right? So in the beginning, if you insert the vortices, the initial perturbations are maybe not the correct perturbations, but it will relax to the right solution.
Exactly. I'm more curious about the radiation here. Did you see some?
So, right, I see some radiation. Yes, we haven't analyzed the radiation. There is some radiation, and we just absorb it at the boundary. But it's very minimal. It's really
okay. But if you can like track it indirectly with the conservation of energy, right? To see how much of it.
Yes, this I can do, but it's really not too much. It's fine. Of course, there is some energy loss. I fully agree.
Yes, because it's vortex, right? Because for a kink case, everything is much more dramatic. But here, everything
here it spreads in all directions, so it's not so important. Right. In the kink case, you have only the excitation. You have the radiation only in one direction, so this can influence also your dynamics a lot. But in this vortex collision, not, because it spreads in all directions.
Good. I don't know. I have time for one more question. I don't know. Fabiano, Manuel.
You can.
It depends.
Okay. There is just one more thing I was curious. Like the frequencies that you're looking, and always reading off from the frequencies going down or up, reading off like the potential barrier or a well to be attractive or repulsive. This was your explanation, right?
Yeah, right. It's very hard.
But this has a hole sometimes. I think, because like if you work with kink with impurity in BPS regime, in different distances you can have different frequencies, but it's BPS. There is no force associated to that. It's just, of course, in this scenario that you're seeing, the configuration is fixed, so it means really a potential that it goes down or up. So you can deduce the force. But this is not always the case. It's just complementary.
Yes, that's a very good comment. Yes, if you have impurities, it's different. There's also a BPS limit with the impurities already included, right? So this is what I mean. Right. No, but here it's really just
in that case, you can't read off the potential like that. It doesn't tell you that there is a force attractive or repulsive, because it's equipotential.
But here it's basically true. Yeah.
Okay. Perfect. Thank you.
Great. You're welcome.
Yeah, my question exactly was about this, related to this. When you have excitation, so that you have an effective interaction, right? So, and the previous attractive interaction, scalar interaction it can change, right? So if you have like in excitations, right? So that's what my question about. So I think you already touched this.
So wait, what can change? Which interaction?
The attractive interaction, scalar interaction.
Yes. Okay. What is? I'm not
For
sure.
example, yeah. For example, in this case of excitations, right? So
Yeah.
if we have excitations, previous they once you have excitations, you have an effective interaction, right?
Yes, I agree.
Related to this, and this
Right.
interaction can change, right? So they can turn change from these attractive to the repulsive. My question is if this is possible.
Wait. You mean I don't really get it. So you mean here? So here, this is the case if we have this configuration here along the
No,
TFS.
no, I don't. I'm not asking about exactly this case. I'm asking about when you have excitations, right?
Yeah.
If you have excitations, you're supposed to have like an effective interaction, right? So once you have these
Effective direction.
yes, effective interaction, like interact. So imagine if you don't have excitations, you're not taking into account excitations, right?
Yeah.
The scalar interaction is attractive, right?
The scalar interaction is attractive. I agree.
It's attractive. Now let's add these excitations. Because
Yes.
excitations, do you think these interactions, attractive interactions, can change?
Okay, good. So, right. So, okay, in the BPS limit, you don't have interactions, right? You have scalar attraction, but also
Yeah, that's
H.
understand. Yes, yes.
But let's take the case where lambda is smaller than 1. Then you have a scalar attraction, right? And we can,
Yes.
for the moment, ignore the gauge part. So in that case, I mean, you have scalar attraction. So if you excite the two vortices in phase, they will just attract stronger because you have on top of this interaction. But there's also the case where you have the out of phase excitation that I showed you before, right? You can excite them like this here, out of phase. Then this yellow line is the relevant one. In that case, you can really find a regime in which they attract they attract by the scalar force, but they are repelled by the excitation. Of course, the excitation decays at some point, but for some finite time interval, you can have a point where the forces at the end even cancel, for example. So this changes. This is something that changes in these dynamics.
Yeah, I see.
But it's just always an effect on top of it, right? You can also have the same thing for cases where lambda is not 1, where you're beyond the BPS limit. Then you have scalar attractions, but on top of this, you have mode interactions.
I see. So this is when you're talking about it. Just you mentioned something on top of that, right?
Right, but here in the full talk so far, I was focusing only on the BPS case where you don't have forces between the vortices.
Yes.
Forces is from the gauge and scalar sector. We have forces from the modes, but not the ones that are there without the modes.
Okay, got it. Thank you.
Okay, perfect. Okay, so yeah, I mean, are there more questions? Otherwise, I would go on with vortex-antivortex collisions, and I have a lot of time also later, so we can also discuss more questions later. Okay, so the second part of my talk is now on vortex-antivortex collisions. So this is something that we, okay, it's actually not 26, it was 25, so this is something that we published last year. And the question is very simple. So let's start first with kinks. So what is known about kink-antikink collisions, for example? If a kink and antikink collides, what will happen is that if the velocity is very low, or if the velocity is very high, let's start with the high velocities, they will just bounce back and separate forever. And this plot is basically describing what exactly can happen. So for high, okay, let me first tell you what this plot means. So here on the x-axis, we have the initial velocity of the kinks. Here on the y-axis, we have the time. And this plot shows the scalar field value at their origin, which means at the collision point, how it changes. It's usually at minus the width, but when they collide, the scalar field changes from the width a bit. and this is always when the color here is getting red. So for high velocities, for example, you have only a single bounce, which means the kinks, they come and then they bounce back and separate forever. For smaller velocities, you can also have some regimes where you have two bounces, for example, at around 0.2 times the speed of light. You have two bounces, they bounce twice, and then they separate forever. Or in the very low velocity regime, you have annihilation into an oscillon, which means the kink and antikink, they are coming, and then they bounce multiple times and form a bionic state. So they form, it's called bion, or some people call it also oscillon in that case. And right, so these are the different possibilities. And what exactly is happening for the different velocities, it depends at the end on the initial velocities. It's very hard to predict this, and no one ever really managed to predict exactly this pattern, which was found numerically from simulations. There are some approaches with some collective coordinates, some collective coordinate approaches, but it's a very chaotic structure. So this is a chaotic structure which is not really easy to predict. But this was found now in the 80s, I think, beginning of 80s. I hope I'm right. And since then, for 40 years, people ask the question, okay, is this something that is unique to objects in 1+1 dimensions, like, for example, kinks? And so people ask, okay, could this, for example, happen in a vortex-antivortex collision? And this is something that we tried to answer. So we took a vortex-antivortex and an antivortex, and we collided them with each other. So why people could expect that something like this can happen? So for this, let me first explain you why this pattern is appearing for kink-antikink collisions. So to have something like this that you just saw, you need always a resonant energy transfer mechanism. And this mechanism describes basically that energy oscillates. There's all the time an energy flow between the kinetic energy of the kink and the mode potential energy. I showed you already before that you can have energy that is stored in the mode itself and energy that is stored in the kinetic energy. Now, when you excite a kink or a vortex, when you excite a kink, this mode is nothing else than an energy flow between the mode potential energy and the kink, the kinetic energy. Which means, okay, the kinetic energy will always grow and decrease, increase and decrease again. So with some specific frequency, with the mode frequency. This means if the two kinks are, for example, coming and they bounce, if after the bounce, the kinetic energy is high enough that they can overcome the escape velocity, then they will separate forever. But if after the bounce, a lot of energy is stored in the mode itself and not in the kinetic energy is low enough such that the kinks will again attract and bounce again. And this is called this resonant energy transfer mechanism. So if something like this appears, if something like this exists, then you can have these chaotic resonant patterns, what I just showed you here. Okay, now because the vortex has a mode, there should be an energy transfer mechanism that is active. So this is something that could appear. And this is what motivated us to study this and see if this vortex-antivortex collision has really also this resonance structure. And what we found is the following. So, okay, first of all, before I show the result, vortices are in general more complicated. One thing is that for kinks, you can rescale your theory such that it doesn't depend on any coupling constants. You can rescale everything out, basically, and write everything in terms of, you can measure everything in terms of the boson mass of the theory, of the scalar boson mass. But for the vortex-antivortex case, now the interactions are lambda dependent. This is what I showed you before. The core sizes depend on lambda, for example, which means you have one more parameter, and this means, okay, it's more complicated to study this, study vortex-antivortex collisions, because now the vortex-antivortex collision not only depend on the initial velocity, they also depend on lambda, on this scalar, on this parameter here. Additionally, we don't work in 1+1 dimensions, we work in 2+1 dimensions, which means that collisions are not necessarily head-on. You can have some impact factor on the vortices. So, but in this talk, I will not focus on this. So we did already some first tests with impact factor, but this is something for the future. Okay, good. Now, we did this collision with the vortex-antivortex, and this plot here basically tells you all the, map shows you basically everything what at the end can happen at this vortex collision. So I will go through this map now in detail in the next few minutes. So what you see on this plot is on the y-axis the initial velocity of the kink and anti-kink, of the vortex and anti-vortex, sorry. And on the x-axis you have the lambda. And the color shows different possibilities what can happen. So let's start first with this gray region because it's the most boring region. So when a vortex and anti-vortex in this gray region, so where lambda is for example 1 and the velocity is very low, then the vortices just annihilate into radiation. So they just disappear. So for very small lambda, there's a paper by Gleiser. He found that for in a vortex-anti-vortex collision, you can also form some oscillon, but this I will not study in more detail here. Okay. Now, another thing that you can notice in this plot is that the scattering always happens in a very high relativistic regime. So you see, okay, the lowest velocity that I'm plotting here is 0.8 times the speed of light, up to 0.97. So, okay, so the gray region is clear. Now let's go to this big light green region and the big light blue region here. So what these two regions describe are basically backscattering and passing through scatterings. So what I mean by this is, if you have an incoming vortex and anti-vortex, so the black dot here is always the vortex and the circle is the anti-vortex. So you can, in the background, I am also plotting the phase in this rainbow plot. So you can see, okay, when the color is changing, if you go anti-clockwise around the vortex, the color is changing from red to yellow, green, blue, purple, back to red. In the other case, it's the opposite way around. So when you go anti-clockwise around the vortex, you have red, purple, blue, green, yellow, red. So you have a vortex and an anti-vortex. So this is how we can distinguish a vortex from an anti-vortex in the simulations. So we just look at the color and see if it's a vortex or anti-vortex. Okay, so now backscattering means that the vortex that is first coming from the left also backscatters to the left. So it also leaves the plane, leaves the collision to the left. Passing through means that the vortex and anti-vortex really go through each other. So the vortex that was coming from the left leaves to the right. So this is what these two events means. And in this plot, these two colors describe exactly this. So for lambda smaller than 5 and very high velocities, the vortices always backscatter. And for lambda bigger than approximately 5, the vortices always go through each other. So this is a result which is not new. This was already found in the 90s by Paul Schellert and some colleagues. They already did these simulations and found exactly this case, that they can backscatter or pass through each other. Okay, let me show you 2 videos, how this could look like. For example, in this green region here, which is close to the yellow here, but still in the green, we really have a vortex-anti-vortex that comes, annihilates, and then recreates and separates forever. What you can also notice in this collision is that after the recreation, you have really, you really see how the kinetic energy is changing all the time. So you have this resonant energy transfer mechanism, right? So you have a mode that gets excited at the collision. So all the vortices initially, so in all the simulations that I'm showing you now, initially the vortices initially are not excited, but at the collision, they get excited. And here in that case, they get excited by the bound mode for lambda around 1. Lambda equals 1, exactly. And you see, okay, after the recreation, they are really excited, and then they move away. Okay, the blue region here means they pass through each other. So in that case, they really go through each other and appear on the other side. Okay. Now let's go to way more interesting cases. And these are the cases with the color yellow. So yellow, or also red, always means that the vortices annihilate in the final state. But before they annihilate, they can bounce several times. So this means, okay, vortex-antivortex, like for kink. A vortex-antivortex can come, recreate, and then they scatter again and bounce and annihilate at some point. So let me just show you some examples, then it's clear what I mean. So if we look, for example, in this region here, this is still a bit darker orange, we can see that the vortex-antivortex bounces 3 times, and then it annihilates and disappears forever. And this can, and what we observed in our simulations is there are parameters up to 9 bounces. So this is a case with 8 bounces, for example. So the vortex and antivortex, they really bounce 8 times before they annihilate. Okay, good. And then besides these yellow regimes, you have also some other colors, this blue and green within this yellow regime. So this big blue teardrop, basically, and some other small windows. So let's analyze one case in this blue region here. This just means that the vortices bounce once or twice, and then they separate forever. So the final state is not annihilation, the final state is separation forever. But before they separate forever, they bounce once or twice. So in this teardrop here, they have this one small bubble here, so they bounce basically twice. So they come, they bounce, and then they bounce again, and then they separate forever. Or you, okay, this is the result, I have it here. So Fabiano reproduced, so this is what he mentioned before. So Fabiano reproduced exactly this simulation. So this case for 0.88 and lambda equals 4,4, he reproduced it, and you can see, okay, this is really exactly the same result. So this is in perfect agreement, and I'm very happy that he reproduced it, because this is also a nice check that the things that we did are really actually right. So I'm always happy when people are also working on these things on which we are working. Very nice. So thanks, Fabiano, for doing this. I just wanted to show this here very briefly. Okay. Now, one more extreme case is, for example, this darker blue case. Here you have 3 bounces, and then they separate forever. And this is basically everything what we found. We never found 4 bounces and they separate forever, but we guess that these regions can also exist somewhere here, but our resolution with which we scanned through the velocities in lambda was maybe not good enough for this. Okay, now let's analyze one full line. So let's choose lambda 4.4 and go along the line for different initial velocities, because this is usually what people are doing for kinks, right? They have the velocity on the x-axis and time on the y-axis. So we want to do exactly the same, and we got this plot here. So you can clearly see it's not exactly the same as for kink-antikink collisions, but you can clearly see, okay, there is some similarity. So we have a regime for high velocities, very high velocity, in the ultra-relativistic regime, where we have a single bounce, we have a window where we have 2 bounces, or here even one with 3 bounces, and then we have also a window where you have few bounces, and then you have subsequent annihilation. So this is basically what we found in all these simulations. But now there's one very important question. Okay, first of all, this is very similar to kink-antikink collisions, but there's one very important question, because I showed you this plot in the beginning of my talk, and I told you that for lambda above 1.5, the mode is above the mass threshold, so there shouldn't be a bound mode. But you saw in this plot here that the most interesting structure is happening above 1.5. So lambda 1.5 is here, so everything where we have a bound mode is in this regime here, but the most interesting things are happening for higher lambda. Now the question is, okay, how can we have a resonant energy transfer mechanism if there is no mode? So here we have a mode, but we don't really see it. It seems that there's still not the structure like for kink-antikink collision. It was for higher lambda. And at higher lambda, we don't have a bound mode anymore, but we can have so-called Feshbach resonances. So what are Feshbach resonances? Feshbach modes. So Feshbach modes always appear when you are above the mass threshold of one field, but still below the mass threshold of the other field. So in this case, you can be, for example, above the mass threshold of the gauge field, but below the mass threshold of the Higgs field. And if the interaction between the modes in the gauge sector and the scalar sector is suppressed, if the interaction is very small, then this mode purely in the Higgs sector, that is not really coupled to the gauge field, can really live forever. Not forever, but for a long time. It's still exponentially decays, but it decays exponentially quite slowly. So you need a weak coupling to the continuum spectrum. So this means, if I go back to this slide, so I showed you these linear profile equations. So F describes the perturbations in the scalar sector, G in the gauge sector, and now what we are assuming for the Feshbach resonances, which is not exactly true, but it's a good approximation, we assume that the interaction terms, so this is the equation for F, and there's a term with the G, so this interaction term, we assume it's just very small, and we completely ignore the gauge sector. So we just solve the equation in the scalar sector, and we ignore the gauge sector. And in that way, you can also find some modes which have frequencies at the end, above the mass threshold of the gauge field, but still below the mass threshold of the Higgs field. So which means there are some modes, and these are these Feshbach modes. They are exponentially fast decaying, but they can still be long enough to activate this resonant energy transfer mechanism in these vortex-antivortex collisions, because these vortex-antivortex collisions really happen in a very short time interval. So they are long-lived enough such that they can influence the dynamics in these vortex-antivortex collisions. And now what we did is, we wanted to check that this statement is really true, and how we did this was the following. So we always took the vortex-antivortex, and after the collision, we measured the frequency from the simulation. And then what we found is that for low lambda, after the recreation, you really have the frequency that corresponds to the bound mode, but for high lambda, you have a frequency that fits more or less quite well to this Feshbach frequency line. So this is just, we did a lot of approximation, so it's fine that these lines don't agree perfectly, but you can see, okay, there are frequencies that are below the Higgs mass threshold, but above the gauge mass threshold, and they're very close to this Feshbach frequency line. Okay, so this was basically the story of my talk. So this basically describes the full map here. So we have the interesting thing in the regime for high lambda because of Feshbach resonances. And in the low lambda regime where you have a bound mode, you have some bounces, but only 1 or 2 bounces, and not really more like this. So let me summarize my talk. So the first part of my talk was about multi-vortex collisions, vortices of same winding. We wanted to see how excitations change geodesics, BPS geodesics, when vortices are excited initially. The second part of my talk was not about multiple vortices, it was about vortex and anti-vortex. And we found there is a multi-bound structure that appears not because of the bound mode, it appears because of Feshbach resonances. And I hope I convinced you in this full talk that resonances really play a crucial role in vortex collisions. So thanks a lot for listening. And if you want to see the videos again, or also videos on, usually I work a lot on magnetic monopoles. If you want to see videos on monopoles, you can check out this YouTube channel here. So thank you.